Welcome back to Interactive Art using Sensors and Light. In our first class, we looked at how to use capacitive touch sensing to trigger sound output. In the second class, we'll learn how to use LEDs to output light. We'll get some inspiration for wearables and installations and learn how to create beautiful lighting animations, moving patterns of light. We'll also learn how to use the three sensors that come on board the Circuit Playground Express, the temperature, light, and sound sensors, to trigger interactive events. We'll continue to develop our C++ programming skills as we learn about float variables, if-else-if statements, and while loops. We've got a lot to cover today, so let's get started. If you're jumping into this course for the first time, please visit mirabellejones.com/hackaday-sensors. Here you'll find links to the GitHub that will have all of the course source code, and also links to the slideshows, which have links in turn. And if you need help getting set up, you can find the slides for Class 1, which will walk you through how to install the Adafruit Circuit Playground board and library, and also how to install Arduino if you don't have your environment set up yet. An LED is a light-emitting diode. When current passes through the LED, it causes the LED to light up. To get to our example sketches, we want to go to File, Examples, and then down to Adafruit Circuit Playground. Here you'll see a whole bunch of sketches that you can use. You can really dig into these to learn how to use the microphone, the light sensor, and more. But for starters, let's just blink this LED. To get to the blink sketch, we want to go to Hello Circuit Playground. Underneath Hello Circuit Playground, there are some introductory sketches that should get you started using some of the onboard sensors of the Circuit Playground. Let's start with Blink. In this sketch, we see that we're including the Adafruit Circuit Playground library. This is the first line of our sketch. Then we have a setup function and a loop function. These are the two main functions in Arduino. In our setup, we're initializing the Circuit Playground, circuitplayground.begin. We'll need to do this every time we want to use any function that's in the Circuit Playground library. Then in our loop, we're saying circuitplayground.redLED high. Then we have a delay of 500 milliseconds, or half of a second. Then we're saying circuitplayground.redLED low, and then have another delay for half a second. What this sketch is doing is it's targeting the red LED, which is D13 on the Circuit Playground Express. This is an indicator LED that's a single color LED, just like the one that I showed in the video. This LED will light up when current passes through, again, just like I showed in the video. So what we're doing is we're saying high, which is sending the maximum voltage that we can to this LED, 255. Then we're setting it to low, meaning that we're setting it to 0, the lowest amount that we can send it. And we have a delay in between. So when we upload this, we should see the LED blink. Let's give it a try. To upload a sketch, you want to go to the arrow at the top. If you hover over this, it'll say upload. You also want to make sure that you have the correct board and port selected. Once you know that this is the case, click the arrow to upload your sketch. You'll see the LEDs on the Circuit Playground go from red, then to green. When they've gone to green, you know that it's been uploaded correctly. Now we can see the red indicator LED, D13, blinking. If you encounter any problems uploading your sketch, you can press the reset button twice and reset your controller. For your first challenge, try going back to the sketch and trying to get the LED to blink at a different rate. As a hint, try using a different delay value. What is a Neopixel? Each RGB LED, or Neopixel, is actually made up of 3 smaller LEDs, one red, one green, and one blue. The combination of these 3 color channels creates the visible color of the LED. When all 3 colors are turned on, you'll see white, and when none of them are, that's black. So black is always equivalent to off. Other colors are created by mixing the 3 color values. You can try this out for yourself by using the Hello Neopixel sketch. Try changing the last 3 numbers in the parentheses to mix the red, green, and blue color values. Let's give this a try. We see our LEDs light up with various rainbow colors, and then they go black. This happens at a half-second cycle. It's nice having source code to use, but we learn best by trying things ourselves. Let's try changing the values in CircuitPlayground.setPixelColor to make our own colors. Can you try changing the pixel number and also the RGB values? In the first challenge, just try making your own colors. Have fun and experiment. For the second challenge, try turning all of them to purple. For the third challenge, try turning them all to white, and then all off, and then all white again. For advanced users, try using a for loop to set the color of all the LEDs at the same time. Or try making your own animations. This principle of finding an example or demo sketch and then experimenting with the functions and also the variable values in order to see what they do will serve you well when learning Arduino. Programmable RGB LEDs use an onboard driver chip to turn the electrical signals on your data wire into programmable colors by setting the red, green, and blue channels accordingly. The library we'll be using, FastLED, can handle most programmable LED drivers. The most commonly used are WS2811, 2812, and 2813. Adafruit's Neopixel line are some of our favorites due to the wide variety of products they offer, but you can also find more affordable products online. Individual LEDs. You can get surface mount, through-hole, and even sewable LEDs online. These can be great for embedding subtle lights into projects or wearables without ending up with an overt light strip look. LED strip, the LED workhorse. Strip comes in densities from 30 LEDs per meter to 144. Higher density strips require more power. Note that LED strip is easily damaged if you don't take care when installing it. It's best to not bend or crease LED strip, so if you take it around a corner, it's best to cut the strip and solder some jumper wires between the two strips. LED modules. These are individual RGB LEDs, each sealed into its own waterproof module with a diffuser. Short wires, typically 4 inches, separate each module from the next. Great for a light bright look or for embedding individual pixels into the surface of complex outdoor artworks. LED matrices. These come in square or rectangular formats. Larger matrices require more power. The LEDs in your matrix can either be wired across like a typewriter or back and forth like a snake. FastLED can address both as long as you tell it which type you have. If your matrix doesn't say, then don't worry. Experimenting is an easy way to find out. LED rings. These come in sizes from about 12 LEDs up to 60. The larger rings require 2 power injections. We'll talk about those later. The smalls can be powered off in Arduino as is. These look cool as they are, but they're also fun to embed inside round objects. They can make cool eyes if you install them in pairs and are careful with the programming. Side-emitting LED strip. These are powerful when you want to use LED strips, but you need to attach the lights to the inside of a solid shape, such as a tube or half dome, or need them to shine out rather than up. Unlike regular flat strips, these strips can bend to an extent without damage. LED neon. These LEDs are embedded inside a thick neon look diffuser. They're quite flexible, making them perfect for lining complex surfaces, using as recessed lighting in a room, or making neon art. Now it's time to make our own animations using the FastLED library. FastLED is a powerful library that allows us to make many patterns and animations pretty easily. If you haven't already, you can download the FastLED library. To do so, go to Manage Libraries and then click Add FastLED. You'll find example sketches from the FastLED library under File, Examples, FastLED. We can use any of the sketches in the FastLED library with our Circuit Playground Express. All we have to do is change the data pin to 8. The data pin 8 is where all the LEDs are wired to. Here's how to install the FastLED library. Go to Manage Libraries, and then in the search bar, type in FastLED. It should be one word. There may be a few options that come up, but we want to grab the first one that's just called FastLED. Select the most recent version and then click Install. Once it's installed, open up FastLED's Blink sketch. This can be found under Examples, FastLED, and Blink. You'll notice that this sketch looks very different from our other Blink sketch. This is because FastLED programs lighting a little differently. First, what we'll want to do is comment out clock pin. We can do this with 2 forward slashes. Then we want to change the define for data pin to 8. 8 is the pin that all of our LEDs on board the circuit playground are connected to. Then we want to change the number of LEDs to 10. There are 10 onboard LEDs. Double check your values, then hit upload. Only one LED is blinking. We changed num LEDs to 10, so why don't all of them work? Here's why. LEDs within FastLED are treated as elements in an array. You can see the array declaration on or around line 14. If you don't have line numbers turned on, you can go to Preferences and then check Display Line Numbers. So on line 13 we see CRGB LEDs num LEDs as an array. This tells FastLED we would like to reserve space for an array of 10 CRGB objects, aka RGB pixels. Note that this line always goes at the top outside of the setup and loop functions. Below, you'll see the following line in setup: FastLED, add LEDs, Neopixel, data pin, and then in parentheses, LEDs, num LEDs. This tells FastLED that you have Neopixels on data pin. They're to be stored in the LEDs array, and there are num LEDs of them. You always need a FastLED.addLEDs call in setup when working with FastLED. There are many options for this line since there are many kinds of LEDs in the world. Check out the other entries for some possibilities. Anyway, scroll down to the loop function, and we'll see why our LEDs aren't lighting up. In loop, our code says the following: LEDs 0 equals CRGB red. Then there's a call to FastLED show, which is a function of FastLED. Then we have a delay of half a second. What this says is, light LEDs number 0 to red, then call FastLED show, then wait half a second before continuing. Then the code does the exact thing to set the LED at 0 back to black, completing our blink cycle. These 3 lines represent the fundamentals of any FastLED sketch: code that changes the values in the LEDs array, a FastLED.show call, and some timing code. At its ordinary speed, the Arduino operates much too fast for humans to perceive, so we need a way to change our lights more slowly. Note that delay is not the way you should do this in non-demo code. We'll explain a better way in the next class. The only confusing thing here is FastLED.show. Use this call whenever you want the strip to update. It'll cause FastLED to write the contents of the LED array out to the actual lights. Often you'll use just one FastLED show call at the end of your animation loop, after you've made all the color changes you want to make. This is important because FastLED.show can be an expensive call in terms of time. If you can call it just once per timing cycle, you'll improve the efficiency of your code. In the case of this demo, however, we have 2 show calls inside the loop, one for the red color change and one for the black. And this also happens to answer our question from earlier. Only one LED is blinking because we're only changing LEDs 0, which is the first LED in our array. Note that arrays always count from 0 and stop at 1 minus num LEDs, in this case 0 through 9. It might seem intuitive to copy and paste in order to get all of the LEDs to show. But this takes a long time. Maybe there's a better way to do this. When you have this many pixels, it's not really practical to copy and paste. Thus, we're going to use a control structure called a for loop to do the work for us. Change your code to look like so. First, we're going to write for, opening parentheses, int, which stands for integer, a number, I, which is a variable, and we're going to start at 0. While I is less than num LEDs, which we already set earlier to 10, then we want to increase it, I++. Now, what we want to do is instead of changing 0 to red, we want to change any LED that is I to red. Then we're still going to do FastLED show and then a delay. Now we want to do the same thing for turning the LEDs off. You can type this out again, or you can copy and paste. Again, we're going to have this for loop, and then instead of changing it to red, we want to turn them off, which remember is black. Let's give this a try. Now let's try an experiment. What if in our for loop, instead of having I as less than num LEDs, we had I less than num LEDs divided by 2. Let's try this for both of our for loops. What do you think will happen? Can you guess? We'll see the first half of our LEDs light up. Let's make another change to our sketch. What if instead of dividing the number of LEDs by 2 for our up to in our array, what if we changed int I to equal the number of LEDs divided by 2? Let's try doing this in both of our for loops. Can you guess what will happen? Now we see the other half of our LEDs light up. By this point, you may have worked out how for loops work. You give them a starting point and an ending point, and instructions to execute at each step of the loop, in most cases I++, which is a shorthand way of writing the most common iterator, I equals I plus 1, aka do this for every entry in the array. Let's go back to our basic for loop. What if instead of having I++, since this means I equals I plus 1, we had I equals I plus 2. Let's try making this change for both of our for loops. Can you guess what will happen? Now we see every other pixel blink. I bet you get the picture. You'll use for loops later on to develop more complex lighting patterns. To read more about for loops, see the reference here. One important thing to remember when experimenting with for loops is that trying to write to an array element which is beyond the end of your array, as defined in num LEDs, may cause crashes, freezes, and other undesirable effects. Likewise, reading beyond the end of an array will return unexpected values, because you're actually reading them from whatever happens to be stored right after your array. These off by 1 errors are an extremely common cause of bugs, even for seasoned programmers. So always check your code to ensure that you don't access any pixels beyond the end of your num LEDs array. When you're finished, save the file. We'll call it Basic LED Playground. You can use it as an example later on. Now let's go further with FastLED sketches. There are lots of ways to animate your LEDs instead of just turning them to one color. A good place to start is with the FastLED sketches in Arduino. To access them, go to File, Examples, and down to FastLED. There you'll see lots of sketches that you can play with, but let's start with Cylon. Here we see a very similar setup to what we had before. To use Cylon or any FastLED sketch with our onboard LEDs for the circuit playground, we want to change the number of LEDs to 10 and the data pin to 8. We can ignore clock pin. Then we see we're creating an array, a sRGB array of LEDs. We've added our LEDs and we've set the brightness to 84. You can change this to any value up to 255. Then we see a function called fadeAll and a for loop. In this for loop, we see we're starting at 0, we're going up to the number of LEDs, and then we're iterating. And then as we're doing so, we're scaling something. Let's have a look and see if we can figure out what that is once we animate it. Then we see a loop that stores a hue value. We have a serial print line statement of x. And then for int I equals 0 and I is less than the number of LEDs, we're going to iterate through the LEDs. And we're going to turn the LED to a CHSV value that is hue++. So we're iterating through hues. Then we're showing the strip, and then we're fading all. And then we see that this goes in the other direction. So what do you think will happen when we upload the sketch? Can you guess what the animation might be? Let's give it a try. We see our LEDs fade through a rainbow pattern. This is happening because we're iterating through hues and then fading. FastLED is a very involved library. To learn more, you can go to the FastLED GitHub page, which has an excellent reference, but we won't be covering everything in this class. If you want to know more about LEDs, Kathy and I have a separate class on FastLED at HackadayU. See the HackadayU website to sign up. Anouk Leprecht is a Dutch fashion designer who creates robotic dresses. Many of them use sensor systems as input, and either servos, LEDs, smoke, or other outputs. The pangolin dress is a 1024 channel BCI, brain computer interface dress, that visualizes brain activity by changing 32 different 3D printed panels, or scales, with 32 implanted LEDs. In this way, the movement and light of the dress visualizes brain activity. Behnaz Farahi is a designer and creative technologist working at the intersection of fashion, architecture, and interactivity design. She's trained as an architect and explores the potential of interactive environments in their relationship to the body. Bodyscape is an interactive 3D printed fashion item that's inspired by the movement of the human body. As the wearer moves, a gyroscope communicates the gestures to an LED lighting control system, and the lighting is visualized as a part of the movement. Behnaz uses 3D printing to create delicate diffusers for the LED lighting that can contour to the body. His research is based on Langer lines, which are the topological lines of skin tension. Bodyscape is an investigation of our relationship between anatomy and materiality. Based in Tokyo, TeamLab is one of the most impressive interactive arts collectives on the planet. They create enormous, large-scale exhibitions in museums, as well as pop-up exhibitions. This installation features tens of thousands of LED strips that hang from a ceiling in an enormous mirrored room. As the viewer walks throughout the space, it's as if they're within a crystalline forest, and different lighting animations activate the space, creating mystical environments. Here's another TeamLab piece, where inflatable sculptures contain tilt sensors, so that when they're touched and tilted, the LED lighting responds. This creates a reactive environment using sculpture. Yayoi Kasuma is an artist from Japan. One of her most famous projects is the Infinity Mirror Room, in which visitors are invited into a small closet-sized space that's lined in mirrors. Strands of LEDs hang down from the ceiling, and when replicated throughout the mirror, create this infinity effect. The effect is to create a large installation in a small space. A sensor is an electronic device that detects and responds to some type of input from a physical environment. There are lots of different types of sensors that can measure and respond to all kinds of input, and this in turn can be used in many ways. For example, we might use proximity or ultrasonic sensors to detect the distance of obstructions for visually impaired persons. Or we might use environmental sensors which can determine air or water quality to make suggestions for city planning. We can also use sensors in our artworks, installations, and wearables to explore and visualize sensor data, making interactive works. Last class, we explored using capacitive touch as a touch sensor, and in the following section of this class, we'll have a look at 3 onboard sensors of the Circuit Playground Express: sound, light, and temperature. We'll also explore how we might trigger lighting and sound output using these sensors. Let's get started. The Circuit Playground comes with a thin MEMS microphone that can be used to detect audio levels. You can read the analog voltage on pin A4, but in most cases we're actually going to want to detect the sound pressure level, which is a pressure level that's taken over time. This will range from 50 decibels to 100 decibels in terms of if it's loud or if it's quiet. Open the sketch to Hello Sound Sensor. You can find this both in your course materials and in the examples, but an annotated version is in the course files. In this sketch, we see a new kind of variable, which is called a float. A float is a variable that has a decimal. This allows us to store more specific data than if we were using an integer, which does not have a decimal. This will make more sense once we see the value. Here we see that we're using our float sound value to store some data. The data we're storing is coming from the Circuit Playground's mic, and it's for the function sound pressure level. We then see a number that's in parentheses. This is because in order to calculate the sound pressure level, the Circuit Playground has to take a specific piece of data and then calculate the result. The kind of data that it's taking is a recording over a period of time. So this is a recording of 10 milliseconds. So it will use these 10 milliseconds in order to calculate the sound pressure level. We can change this if desired, but for now let's leave it at 10. Then we're seeing a serial print statement that's printing out the sound sensor sound pressure level, and then also printing the exact value. Then we see a short delay of 90 milliseconds. Let's upload this and then try making some sounds. If we open Serial Monitor under Tools, we'll see the sound pressure level. As I'm speaking, you can see that the sound level increases. The baseline looks like it's about 58.89. This might be a little different for you depending on what kind of environment you're in. When I'm speaking, it goes up to about 62.41. To see this increase more clearly, we can look at the serial plotter. This is next to Serial Monitor under Tools. If you open this up and then try speaking, you'll see that the value increases when I'm speaking. Try clapping, yelling, and talking and making other sounds to see how the sound pressure level changes. To learn more about the sound sensor and how it works, see the Adafruit website's reference for sound sensor. To add interactivity, let's use the if-else statement we used in the last session. Open up ifelse.eno. In the sketch, we still have a float for our sound value, but we also have a float for our threshold value. This is the value at which we are triggering our interactivity, meaning we've decided it's the right volume level to trigger our lighting, or our text, or whatever our output is. I've set it to 65, but this will change depending on what your specific sound environment is. Next, I'm storing the sound value and taking a reading of 10 milliseconds. On line 18, I have an if-else statement. This is what will be responsible for triggering our interactivity. The first part of the if statement says, if the sound value is greater than our threshold, meaning if it's above 65 decibels, then we want to do something. In this case, we're saying serial print line sound detected. Serial print statements can be really useful for holding interactivity. Later we can change this code to actually trigger our output, be that LED lighting, sound, etc. Then we have an else statement. So this means that if the sound value is not above the threshold, then it will print silence is golden. So one of two things will be happening all the time. If we didn't want anything else to happen, we could also comment out this line, and then it would only print sound detected when a sound was detected. Let's try this out. If we open up Serial Monitor, we can see the statement, silence is golden. Then when I speak over the mic and make a loud sound, it says sound is detected. You'll notice that sometimes it'll detect the sound continuously, and sometimes it'll have silence is golden between the print statements. This might mean that our threshold is too high or too low. To make sure that our threshold is at the correct value, we can uncomment the lines 15 and 16 to print out the sound value. That way we can make sure that our threshold is set correctly. Let's try uploading this and seeing if we can adjust the threshold. Now when I go to Serial Monitor, I can see what the value is when I'm speaking. It looks like when I'm speaking, the value is about 62 or so. So if I adjust my threshold to be 62, and then re-upload my code, now I should get a more faithful result. I could also lower the threshold so that it's more sensitive. I think you get the idea. Now it's time for two challenges. First, see if you can adjust the threshold to trigger sound detected only when you're speaking. If you have trouble doing this, see the last video. For a second challenge, can you change the code so that instead of saying sound detected, it lights up the LEDs? As a hint, try copying and pasting the for loop from to for loop or using to hello Neopixel. For advanced students, try triggering a FastLED animation. To solve this challenge, I'm going to look and see what I need to replace from the LED for loop sketch within my if-else sketch. So right now, I see that when the sound value is over a threshold, it prints sound detected. This is a placeholder for my interactivity, so I know that this is where I want to put in the for loop that'll turn on my LEDs. I can even write pseudocode to remind myself that this is where I should put it. Then I can either decide to just leave them on, but maybe I want to turn them off when I'm not speaking. In that case, I want to use the else statement. So instead of printing silence is golden, I want to turn off the LEDs. Now that I have my pseudocode, I can find the code that'll actually make this happen in my for loop code. Here we find the for loop for turning on our LEDs by setting the pixel color to purple. I'm going to want to copy and paste the entire thing and put it where it says turn on LEDs. Now I want to find the code to turn off the LEDs. And I know that it's circuitplayground.clearpixels. I'm going to copy that line and I'm going to put it in where it says turn off LEDs. Let's upload this and give it a try. Now I see that if I'm speaking, the LEDs light up. Otherwise, they're off. The Circuit Playground Express has an onboard light sensor that's connected to analog pin 5. You can use analog read or you can use the light sensor function from the library in order to read the value. The value will be between 0 and 123 with higher values corresponding to brighter light levels. The range is approximately 0 lux to 1500 lux maximum. Because average daylight is 10,000 lux or so, this sensor is best suited for indoor lighting. An average indoor light level will be about 300. We'll use the following sketch in order to tell what the average light level is for your environment, as well as what is dark or bright for your environment. Open the sketch Hello Light Sensor from either your course files or from the Adafruit Circuit Playground library. Upload the sketch and try putting your hand over the Circuit Playground, then taking it away to see changes in the data in Serial Monitor. So in the sketch, we're storing the light sensor value as a integer, int value, and then we're updating that in the loop by calling circuitplayground.lightSensor. We're then printing out the light sensor and the value, and then we have a delay of 1 second. So it's taking readings pretty slow. We could update this if we want to take the readings faster. Let's have a look at Serial Monitor and see what the default reading is for this room. So you can see that the reading is pretty stable. It's either 197 to 199. So today is an overcast day, which is typical in Copenhagen. Not a lot of light in the room, pretty dim. If your room is brighter, you probably have a light reading of about 300 or so. And if it's very bright, it's probably above that. If it's lower than that, I'm guessing that it's nighttime where you are at, or it's very dim lighting. Now when I put my hand over the sensor, you can see that it drops down to about 40. This is with my hand completely covering the sensor. If I put my hand on the Circuit Playground, it drops down even further, and now I'm just getting a single-digit reading. If I hold my hand over the sensor, I get a reading of about 100 or so. So you can see how you might start to play with these values as thresholds in order to trigger different kinds of interactivity depending on how light or dark something is. You can also in this way use a light sensor as a proximity sensor, because if light isn't shining on the sensor, then you know that something is blocking it. So in this way it can kind of be used to detect motion or an obstruction. There are other sensors that do this more efficiently, but unfortunately the Circuit Playground doesn't have any other proximity sensors on board. So the light sensor is a good candidate if you're trying to see if something is in the way of the sensor. From your course files, open the sketch to light sensor, if else. In this sketch, we have 3 different variables. We have a light value, and this is the variable that will store our light sensor value. Then we have a variable for average light and a variable for bright light. So these are 2 different threshold values. So we've decided that average light is anything between 150 to 550, and then bright light is 550 or above. Anything that's under average light would be low lighting. So let's take a look at how this might work if we wanted to have 3 different thresholds. First, we still want to update the variable for light value every loop, and that is taking the reading from the light sensor and storing it as light value. Then we're going to print the value, and then we have an if, else statement. So we've seen if and else before, but now we're seeing else if, which is a third condition. And this is a program, so it's going to be computing this in order. So it's first going to check the if statement, then it's going to check the else if statement, and then it's going to check the else statement. So first it checks, is the light value, which again is our reading from the sensor, is that greater than or equal to the value for bright light, which again is 550. If it is, then we're going to have it print bright light. And then we're also going to have a for loop where we set the pixel color to red. And that's for each LED. Then we want to check if it's medium light. So we have this else if statement that says, else if the light value is less than bright light and the light value is above average light. So this is checking to make sure both of these conditions are true. And this is how, this double ampersand is how you do an and. You can't use a plus because a plus is a mathematical operation. So if you used a plus, it would try to add these two together. So we have to use this combination of two ampersands to make an and statement. But it's basically saying, if this is true, and if this is true. So if both those things are true, then we want to print medium light, and then we want to set all the pixels to green. Lastly, we want to see if it's low light, and we don't have to check that because we know if these two things aren't true, then it's going to be low light because it's the only option that's remaining. So if it's low light, it'll print low light, and then it'll set all the pixels to blue. And then we have a delay of half of a second, and that's between every check of this whole loop. So let's try it out and try to put our hand over the sensor at varying distances and see if we can get those three thresholds to work. You might have to adjust these numbers so that they're more accurate to your lighting environment, but the goal should be that when your hand is not on the sensor and there's bright light, then it should have its own threshold. And there should also be a threshold for average light. So if your hand is hovering above the sensor, it should be whatever this value is. And then low light would be if you have your hand covering the sensor completely. So let's give it a try. The circuit playground also comes with a temperature sensor. It is a thermistor, which is a resistor that changes its resistance based on the temperature. It's easy to calculate the temperature based on the analog voltage on analog pin A0. There's a 10K 1% resistor connected to it as a pull-down, and you can read the analog value and calculate the temperature with the beta constant, or just use the Circuit Playground library. The Circuit Playground library has a built-in circuitplayground.temperature function, which will give you a floating point number in centigrade. Also, if you need to use Fahrenheit, they have a built-in function for that as well, which is circuitplayground.temperature_F. We'll have a look at both of these. Open up the sketch Hello Temperature. In this sketch, we have float variables for both the temperature in Celsius and the temperature in Fahrenheit, temp C and temp F accordingly. In our loop function, we're updating the values for each variable. Then we're printing out the data. There's a 1 second delay between readings. If we upload the sketch and then open Serial Monitor, we can see the temperature readings for both Celsius and Fahrenheit. Up until now, we've been using sensors that are pretty easy to adjust, like light and sound. But how do you change the temperature? Try to get your temperature sensor to display a different value. Here are a few potential solutions to this challenge, but there are probably many more. One is to use fans or heaters to heat or cool the sensor. Another solution would be to take your Circuit Playground Express outside and get a temperature reading from there. You could also bring your Circuit Playground into different rooms in your house. You might also put your Circuit Playground between your hands. Lastly, you can try breathing on the sensor. Give this a try and see if it'll detect a difference. In this way, you could use the sensor as a breath sensor. Have a look at the birthday candles example under microphone demos in the Circuit Playground library to see how this might be used. The Circuit Playground Express has 8 general input-output pads that are available for us to attach our own sensors and our own outputs, such as servos, which we'll get to in the next class. Inputs and outputs are at the heart of interactive design. With interactive design, we take in some data or stimulus, usually from a sensor or a button or a switch. Then we output a response. This could be lighting, sound, or smoke, as seen here in a Nucleprex smoke dress. So far we've used a few inputs to trigger a few outputs. Can you think of all the inputs we've used so far? We've used the capacitive touch, the microphone as a sound sensor, the temperature sensor, and the light sensor. For outputs, we've been able to trigger print statements, LED lighting, and sound from the onboard speaker. But this is just a handful of options. Can you think what other inputs and outputs there are? Which inputs might you want to use in your project? What about outputs? In the next class, we'll look at developing more complex interactivity using an interactivity matrix. But for now, feel free to explore places like Adafruit and SparkFun to see what sensors there are and what you might want to use in your projects. You can also consider different outputs you might trigger and look for tutorials that cover how to use them. So far, we've looked at a few kinds of loops. There's the setup loop and loop function for our main Arduino sketch. There's also a for loop. There's also a while loop. Open up to while loop. This sketch looks very familiar to our if-else sketch. We're still storing the value of our light sensor in an integer, int value. We also have a threshold value, over which we will trigger our interactivity. Then we see that in our loop, we're updating our value variable to store the reading of the light sensor. This is followed by a delay of 1/10 of a second. Then we have a while loop. While our value, meaning the value from our light sensor, is greater than our threshold, in this case 100, we want to print the line trigger interactivity, then have a short delay of 200 milliseconds. While this is true, this will continue to run. When it is not true, it will exit the loop and then go back to a delay of 1/10 of a second. Then it will check once again the value of light sensor and update it. Let's give this a try. So I'm going to start with my hand over the sensor because I know that when it's light, it will trigger the interactivity. So right now my hand is on the sensor, but if I take it off, I'll see that it triggers the interactivity. If I put it on again, it will stop. If I take it off again, it'll start again. As a challenge, try changing the threshold to trigger the interactivity only when it's a certain temperature. As a second challenge, try replacing the serial print line statement with code that will turn on LEDs or play a sound. To solve this challenge, I'm going to open up both my while loop sketch and also my hello temperature sketch because I'm going to want to combine elements of each of them. And before I get started, I've decided that what I want to do is I want to trigger my while loop while the temperature sensor is at or above my body temperature. And so I'm going to first figure out what that is by running the hello temperature sketch and then looking at what the read is for temperature in Fahrenheit when I blow on the sensor versus when I don't blow on the sensor. Once it's uploaded, if I open up Serial Monitor, I can see the reading. Now when I blow on my temperature sensor, I see that the temperature goes up to about 80.64. So there it was 80.82. And that time it went up to 83 almost. So it looks like what I'm going to want as a baseline is any value that's less than 80. And then if it's over 80, I'll consider that to be triggered. Another way to look at this would be to use the serial plotter. In the serial plotter, I see the data coming in. This is without me doing anything. And then we see a spike when I blow on the sensor. And you'll see that there's two graphs. There's one for temperature in Fahrenheit and one for temperature in Celsius. So if I wanted to see just one of these values, say for example, Fahrenheit, I could upload this again. And now when I go to serial monitor, I just see the temperature for Fahrenheit. And then when I go to serial plotter, I just see the value for Fahrenheit. And I can see that a normal baseline is somewhere below 81. And that when I breathe on the sensor, it goes above 81. So I might, if I want to make the instrument really sensitive and if I want to reduce the incidence of false positives, meaning results that say that the sensor has been triggered or is above the threshold when it isn't, I might want to set my threshold to something like 81. I'll do this test a couple more times just to make sure that that's accurate. And sensors are very obviously sensitive to the environment that they're in. So the value may change a little bit depending on where you're at. So that's something to keep in mind. You might have to reset your threshold. Now that I know that my threshold for my temperature is about 80, I can save this sketch as while loop challenge before making changes to it. And then I can change my threshold and we'll say 81. And instead of having int value as my variable, I need to store a float because the temperature data is stored as a float. So I'm going to store it in Fahrenheit and steal this float tempf and copy float tempf in place of where our value was previously. Now I need to make sure that that is changed throughout my sketch. So to start with, I'm also not getting data from my light sensor. I want to update the variable for tempf with the temperature. So I'm going to go and take the line that says tempf equals circuitplayground.temperature f. And I'll take that and place that where value was. So now I'm updating the temperature variable every time. And then I'm not comparing a value anymore. I'm comparing a temperature rating. And then I also want to update it while we're in the while loop. So I'm going to replace this line as well. And this is important because the while loop won't exit until it has a condition for exiting. So the condition here is if the temperature is not greater than the threshold, then it exits the loop. But how will it know that unless it takes the reading? So you have to take the reading within the while loop as well as outside of the while loop. That's why it's written twice. And then here we have a serial print line statement to trigger interactivity. And let's just test this before we put in lighting or sound. I can see that it's saying to trigger the interactivity constantly. So I know that maybe my threshold is too low. So let's try setting this to 82. And there I see that it isn't triggered. But when I blow on the sensor, you'll see that it prints trigger interactivity with a small delay. So to solve the other part of this challenge, which is to replace serial print line with either lighting or sound, I can either put in a for loop for lights or I can play a tone. So if I can't remember how to do that, I can open up my class files and I can open up my LED for loop. I can also open up Hello Speaker. And to play a tone, what I'd want to do is copy the line circuitplayground.playtone, and I want to paste that where interactivity is. And I'm going to make this a fairly low tone that plays for 2 seconds. And then I also want to put in a for loop for changing my lighting. So I'm going to copy that from our LED for loop sketch. And I'm thinking of the sequence here. So first it will print trigger interactivity. Then I want it to set all the pixels to this color, and then I want to play the tone for 2 seconds. The order does matter here because this is a compiled language, and so whatever is written first will get executed first. So if I put serial print line trigger interactivity at the bottom here, that will be the last thing that gets executed, and it will happen after playtone. Feel free to copy and paste these and put them in different locations to see that happening. But for now, let's upload this and see if it works. For homework, and as a final challenge, try making changes to your while or if-else sketch to create your own interactive events for the light or sound sensor. You might also use the temperature sensor or capacitive touch. Then, start to plan how you might install your circuit playground. Would you put it in a wearable or a sculpture? How might that affect your data? Grab materials and start rapid prototyping. Materials could be things like fabric, paper, hollow toys, clothing, and so on. Try installing the circuit playground using these materials and see how it affects the data. See if you can write a program that uses your input and produces an output. The output could be lighting, sound, or pseudocode for some other form of interactivity. If you're out of ideas, try creating a lamp that does different animations at different times of the day. We've covered a lot in this second class. We've learned all about LEDs and how to create responsive lighting. We've even learned how to create animations using the FastLED library. We've also learned about inputs and outputs, as well as how to use 3 new inputs: the temperature sensor, the light sensor, and the microphone as a sound sensor. We've expanded upon our growing knowledge of C++ by using if-else-if, while loops, and float variables. We now have all the tools we need to create a simple input and output program, which takes in data from a sensor and triggers lighting, sound, or print statements. In the next class, we'll go even further with inputs and outputs by looking into using buttons and switches for control and servos to make projects with moving parts. We'll also look at multiple inputs and outputs using more complicated logic and programming. See you next time!